Welcome back, everyone. Did you have a good 3-day weekend? Awesome. Good. Slept all the way through the weekend. Huh? Yeah, me too. All right. So today we get to if you if you're here for the Friday, there was the test corrections. I'll pick if you haven't turned them in, I can get those at the end of once we finish going through 3.3. If you weren't here, if you can have time tomorrow to work on them, and then just get them into me by Thursday, so I can get those updated and get grades posted for those for this week. Any questions before we get started on 3.3? What's that? What's this on? Oh,
yeah, Senior Hummus.
oh that.
You man.
Good eyes. Thank you. I would have had a dead battery. Okay, thanks. Yeah. All right. So we saw each other Thursday, right? And we talked about what kind of probabilities. Does anyone remember what those were called? Conditional probabilities. And those were the probability of two things happening. So A and B. So those are what I call AND probabilities, right? Both happening together. Today, we're going to look at the probability of two things, but OR probabilities, A or B. A or B, or both together, I guess, could happen. But so that's 3.3, the addition rule. We're going to see how that works. And then basically, we'll be done with probability. The last section, 3.4, is applications. And what I'll do is on Thursday, I'll have a worksheet with some sample problems and maybe even some from the homework. Tomorrow, you'll be able to work on the 3 homeworks we've done, 3.1, 2, and 3. So be a work day for that. And then Thursday, we'll also have a time to kind of just directly get into some applications of what we've been doing. But not really anything new, just applications of what we go through. So today's kind of the last part. Let's see. I get disconnected? I did. There we go. Okay, so first of all, we have to, if we have OR probabilities, we have to decide, we have to determine whether the two events can happen together or not. That's called mutually exclusive. Does that make sense? I don't know why they couldn't just say exclusive, but mutually exclusive. So one does, if one happens, the other can't happen. So the sample space for that is that something like event A is completely different from event B, and there's no overlap. They can't happen at the same time. Okay. If they are not mutually exclusive, then they could happen at the same time, or they could happen separately. And we'll talk about, you're going, well, how could that happen? So we'll talk about these type that are not mutually exclusive. And then if we can determine what one or the other, then we know how to count the events or the probabilities. Okay. And basically where we're going is if they're mutually exclusive, to figure out whether A or B happens, we just add the probabilities together. But if they're not mutually exclusive, notice this overlap. If you just add them together, you're double counting that space. And so we've got to subtract off that extra space we counted twice. So that's all there really is to today's lesson. So mutually exclusive or not. Here's two events. We roll a 3 on a die. Is event A B is rolling a 4. Could those both happen at the same time? No, you either get a 3 or you get a 4, but you don't get both. You know, you roll 2 dice, you could, but with 1 die, you either get a 3 or you get a 4, or you get something else, right? So these are mutually exclusive. So would it make sense if we're calculating probabilities for rolling a 3, 4, we would just add them together, right? Probability of rolling a 3 is 1/6. Probability of rolling a 4 is 1/6. Probability of rolling a 3 or a 4 is 2/6, which reduces down to 1/3. Okay, so that kind of makes sense. It's just a way of counting. And because they're mutually exclusive, that's all we have to worry about. How about these? Events are mutually exclusive. So randomly selecting a male student, and in event B, randomly selecting a nursing major. Why not? Very good. So we could select that person, and they're both. So you could be a male student and a nursing student at the same time. Okay, so these are not mutually exclusive. And we'll see how we have to handle that. We basically do the same thing. We can add those probabilities, but then we would have to figure out what's the probability of being both and subtract it off, because we're basically counting them twice, right? If we just add the probabilities. That's all it is to it. Good. How about this one? Then A is randomly selecting a blood donor with type O blood, randomly selecting a female blood donor. Exclusive, mutually exclusive or not? Not exclusive, because we could get a female donor who was type O. So there could be overlap, just like the last one. Good. And so here's the rules that we're going to go into. If they are mutually exclusive, it's sort of easier. We just add the probabilities. And notice it's really the same formula if they are not mutually exclusive, but we just have to subtract off the parts that are overlapping. We have to figure out the probability of being both and subtract it off, because in effect we're counting it twice. Okay, and the probability is really just counting, the simple fact of counting, but we've got to make sure we're counting the right things and that we're not counting something twice or 3 times or 4 times. But that's what we run into is how we count. Okay, so let's take a look at this. You select a card from a standard deck, find the probability the card is a 4 or an ace. Now, again, if you haven't used a deck of cards, but how many 4s are in a deck of cards? How many aces are in a deck of cards? Are there any cards that are both a 4 and an ace at the same time? No, they're not. So those are mutually exclusive, right? And so find the probability. Well, to get a 4 is 4 out of 52. To get an ace is 4 out of 52. Since they're mutually exclusive, we don't have to subtract over getting a 4 and an ace at the same time. So our probability is simply 16 out of 52. Remember, with fractions, common denominators, you don't add the denominators. I almost was going to say 104, but you don't add the denominators, right? What's that? Oh, yeah, I multiplied, didn't I? So that's the other part, and that's a lot of, I'll do this as when I'm supposed to add. I multiplied. Thank you. Did anyone else catch that? You say, well, oh, he's a college professor. He must know what he's doing. But he can make his mistakes just as easily as anybody else. Thank you. 8 out of 52. Okay, which reduces, and we turn to percentage. But this, the process makes sense. We just add the two together. Okay, because they're mutually exclusive, that's all we have to do. Okay, now this, you roll a die by the probability of rolling a number less than 3, so that's one event, or rolling an odd number. Can we roll a dice and get a number less than 3 and an odd number at the same time? Yes. Which number is it? 1. not 3 because it has to be less than 3, right? So that would be 1 is the odd one. So there is this overlap. And I'm going to show you there's kind of 2 ways we can actually do this. We can use the formula, which just says, okay, what's the probability of rolling a number less than 3? Numbers that are less than 3. So that would be 2 out of 6. And notice I don't reduce while I'm just because keeps common denominators. And then what's the probability of rolling an odd number? Well, there's 3 odd numbers, 3 out of 6. But then what we have to do is, oh, wait, there's this overlap region. Let's subtract that because we counted it twice, right? We counted it when we counted less than 3, and we counted it with the odds. So we could do it. This is what the formula tells us to do. Okay, 2 plus 3 is 5. I didn't multiply this time. Minus 1 is 4. So that gives us a total of 4 out of 6, which reduces down to 2 out of 3. Now, there's another way to do this, though, and this is just count carefully, right? I could have said, well, less than 3, there's 2, 6. There's a 2 out of 6 possibility. And then when I go to count the other one, I can say the odds, well, that's 3. Oh, but I've already counted this, so I'm only going to count the new parts, which is 2 out of 6, another 2 out of 6. Okay, which is 4, 6. Which reduces to 2/3. Notice I get a correct answer in both cases. So when it's a small number of things, I just kind of just count carefully, right? I can do that. The thing is you want to remember that formula because sometimes when we have large numbers of stuff, the way they give us the information, it's really hard to figure it all out. So you come back and you subtract off the piece, okay, the overlapping piece. And we've got a couple examples in here that's kind of the easier way to do is just subtract off the middle piece. So far, so good? Okay, so it's 2 things occurring. Again, it's only one, but it's an or, so it's throwing in, there's multiple things that can happen. Right? Frequency distribution shows the volumes of sales and the number of months in which a sales representative reached each sales goal during the past 3 years. Find the probability that the sales representative will sell between 75,000 and 124,000. Okay, 75,000. So how do we go about doing that? Well, they're only going to sell one value, right? But the way the data has been given to us, frequencies, what do we need to use to fit this range of values? Well, I'll give you the first one, right? 75 to 999. That certainly, these 7 people would be in that range. But is there another set of that would also fit that range? Yeah, the one right below it. So again, it's kind of, oh, we got to add these 2 together. Are these mutually exclusive? Yeah, there's no overlap, right? This one ends at 9999. This one starts at 100, so there's no overlap between the 2. And so it's just mutually exclusive, just add the probabilities. And you could just go, well, that's 7 plus 9. Remember, they have a common denominator. They didn't give it to us, so I guess we have to add it. It's 8, 14, 21, 30, 35, 36. Did I get that added together right? So we just add them together and we get 16 out of 36, which again will reduce. 4 goes into both of those, doesn't? 4 goes into 16 4 times. 4 goes into 36 9 times. Okay, so make sure mutually exclusive, just add them together. So This one, blood bank catalogs types of blood, including whether it's Rh positive or Rh negative. Given the donors during the last 5 years, the number of donors who gave each blood is shown in this table. So we got, and a lot of times when we're doing statistics, we look at tables of values. Find the probability the donor has type O or type A. So are those mutually exclusive? Yeah, you can't have type O and type A. And so we're looking at this column here and this column here. They're mutually exclusive. It doesn't mention anything about being positive or negative, so we take these as our total values and we divide the total of everything, right? The sample space is 409. So it would be 184 plus 164. Again, you could put them each under 409, but it also works this way, right? So that's 8 for 348 out of 409. Okay, nothing to subtract off because they're mutually exclusive. So you can, a lot of times on the tables, you can easily see that. So far, so good? Or probabilities. Okay. What about this one, though? This one, we want the probability that they have type B or, and that's an or probability, or they're Rh negative. Now watch on the table itself, you can kind of see whether they're, what do you think? Are they mutually exclusive or not mutually exclusive? Not, because there's a place where we get overlap. Here's type B and there's Rh negative. There's that middle, those 8 are getting counted twice, right? So we could, again, the way they show to do it is you get the 45 from type B, the 65 from Rh negative, but then we're going to have to subtract off that 8 because it got counted twice. It got counted in both of those totals. So again, 45 out of 409, 65 out of 409, and then subtract off the 8 out of 409. And again, this is where it's, you know, you're going to subtract off the 8 someplace, right? So you could have done it, taken it off the 45 and then added the 65, but either way, that gives us 110 minus 8 is 102 out of 409. Does that make sense? Okay, so tables, I like when they give us data in tables because you see those overlapping places or non-overlapping. It's real easy to see what they're talking about. And again, also, if there was a conditional probability, which we did last week, right? Tables work real nice that way. So far, so good. Okay. Looks like we're getting close to the end. I've got one more after this, but this might be a slide that I don't know. Okay, yeah, you got it right here in your booklet. So it just summarizes everything we've done. So let's kind of take a quick look. Remember, probabilities is about counting total sample space, counting the event, number of in the event, and then dividing, right? It's a very, yes. Oh, have some people got cut off. Some people, oh, a lot of you. Okay. Shoot. Oh, but yours.
That was the wrong one.
Oh, maybe you go to the next lesson. I think it's. Oh, that's a different table. Okay. Well, there's a slide. That's why I give you the slide deck too. So you'll be able to take a picture of it or screenshot it, or you can get this from Canvas. So this is, yeah, I apologize for that. Probably when they was getting copied, one of the pages slid out or something. Or, yeah, something we'll watch for next time. Okay.
You guys want a copy of that? I'll work on that.
Okay. See, ask and you shall receive. So, the other thing is, working with frequency tables, probabilities are always between which two numbers? What's the biggest probability we can get? 100% or 1. Remember, those numbers go together. What's the smallest probability we can get? 0 or 0%. You can't have negative probabilities. It either doesn't happen or it happens. Okay, and something in between. Good. This is the complement rule. Sometimes we know the probability of rain. We can also calculate the probability not rain. So whenever two things are complements of each other, either it happens or it doesn't, we can subtract from the 100% or the 1, and we're there. This is what we talked about on Thursday, was dependent events and conditional probabilities. And this is what we talked about today, mutually exclusive events. And that's pretty much all of probability. The rest is going to be applications of these concepts. Okay, so we'll get you the summaries. Basically, all you need to know about probability, and then the rest will be applications. So you've got it. This picture looks like it's all there. This is just I looked at that, I said, what's that going on? It's a graph, but it's a way of showing, this is for the NFL draft. It's showing us that there were 255 players selected, and then it's showing us what positions those players played based upon how many, a layout of a football team, was it 11 on each side, right? 11 on offense, 11 on defense. So together, the probability that a randomly selected draft pick is not a running back or a wide receiver. Now, are there any draft picks that were both a running back and a wide receiver? Got the little kid. So we got running backs here that there were 16, and then wide receivers. Where are they? Oh, they're over here. 37, and I guess they do by primary position. I guess there could be someone who played both positions, but they would have one that they were primarily linked up to. We don't have any listed here. But we want the ones that are not a running back. So does that mean we have to count all the other ones that are not there? Yeah, if you want, you could do it the hard way or the easy way. So the hard way, you could count them all. But since they gave us the total up here, we can say, okay, running backs and wide receivers, we're using an or probability. So 16, I think I just need a, out of 255, plus 37 out of 255. And since there's no overlap, we don't have to subtract anything. So that's kind of what today's lesson is. And then once we calculate that, since we don't want these, we get the complement, we subtract it from 1. Okay. That looks like, wow, that was fast. So that's 40, 13, that's 53 out of 255. And this way to write 1, it's as a fraction will be 255 out of 255. And so now we can easily subtract the 53 from the 255 and say that's 202 out of 255. Which can also be written as a decimal or a percentage. But notice the subtraction was much easier. You added two numbers and subtracted. Rather than going around and adding all of these together, which would have just taken more time. Again, give you the right answer as well. And if you wanted to, you could come back and double check all the, well, 50 defensive backs were taken up in that one. But you could add all these up, and they need to add the 202. So there's a nice way to do a double check, right? It's always, especially if your information is going to go public, you want to have it double checked as much as possible. So does that make sense? Okay. And again, what's nice is it shows a creative way of graphing out data. I've never seen it like that before, but kind of cool. Kind of cool. Questions? There's no more slides, which means we have our lesson, and you should have your thing. So what would be a good idea now is go make sure they're there, start into the homeworks. Hopefully you've already gotten a little bit started 2.1 and 2.2, 2.3. Tomorrow, oh, sorry, get my numbers mixed up. 3.1 to 3.3. Neither one of us will be here tomorrow. Yeah, so you're on your own. Work with each other, but just work on getting as much of that homework done as you can. Okay, and then we'll do a worksheet on 3.4 on Thursday, and kind of get into that together. Does anyone still have their test corrections to turn in? I'll go ahead and pick those up. And yeah, or you could do it Thursday. Oh, yeah, if you've already got it turned in, then I've got those. As long as you got your name on both, it's good. Yeah, I'll keep them together. All good. Awesome. Thank you. Perfect. Still working on it?
Dr. Mike, I
Yes.
forgot how to find the
Z-score is x minus the mean divided by the standard deviation. And you actually got the right number, but it's negative because x is, let's see on this one, x is 9 minutes, the mean is 15. You subtract them, that's a negative 9 minus 15. You'll still get this value, but that's why C is. So you must have probably done it right, but a lot of people did that. They when they subtracted, they just put the positive. It should, those who put their work, that's what I was seeing a lot. That, yeah, that'll help. Perfect. Thank you so much. All good? Awesome. Thank you. You got name on both. Perfect.